Hello, everyone. Welcome to Physics Lab experiment number 8, which is going to be on geometric optics. And in particular, we're going to talk about reflection and refraction. So most of this, there isn't a lot of equations I need to derive for this lab. So most of this I'm going to explain by going over the handout that I created for you guys. So let me bring that up right now. Okay, so here's the handout for lab 8 and again, it's on reflection and refraction of light. So for the first part 1, we're going to look at how light is reflected off of mirrors, off of flat mirrors, like they're called plane mirrors. Now, there's something called the law of the rectilinear propagation of light, and you can think of that as just being that light travels, or you can model it as traveling in a straight line when it's traveling through some medium. So if it's traveling through air or traveling through water or traveling through glass, you can model it as a ray traveling in a straight line. Okay, now what the law of reflection says, so here is a mirror, but this could also be a boundary between two mediums. Like this could be air, and on this side could be water, or air and glass. In this case, I'm just going to think of it as a mirror. So this is the mirror. And I have a ray of light coming in, right? So again, I can think of it as traveling in a straight line. So this is what's called the incident ray. And then it's going to hit that boundary, and it's going to reflect, or if it's a boundary between two mediums, part of it will reflect. So in this case, since it's a mirror, most of it is going to reflect back off of that boundary. And if you measure the angle of incidence, which is called theta, and you measure the angle of reflection, right, which is called theta prime in this case, and those angles are always measured relative to a line that's perpendicular to the surface. So this dashed line right here is perpendicular to the mirror, right? So the incident ray is measured relative to that normal line or perpendicular line. And what you should find is, in theory, the angle of incidence should equal the angle of reflection, okay? So in the first experiment, you want to go and view my videos on how I collected the data. So I collected all this data for you. These are the links. So you have the links. I will also post the links separately in Brightspace, but you should be able to, if you download this Word document, I think if you control and click on that link, it should take you to that YouTube site. And basically, I measured, bring up the table here, for 4 different conditions, right? 4 different angles. I had the laser coming in at a particular angle of incidence. So these are my angles of incidence. And I measured the angle of reflection for those 4 cases. So what you guys have to do, and this is question 1, is you have to calculate the ratio of the angle of reflection to the angle of incidence. So that's this theta 1 prime over theta 1 is. So you're going to divide the angle of reflection divided by the angle of incidence. And then you want to compare it to the gold standard, right? But what is the gold standard? Well, remember, in theory, the angle of incidence should equal the angle of reflection. So the gold standard for that ratio should be 1. So you want to compare your results to 1, and you want to compute a percent experimental error for those 4 conditions. Okay, and hopefully they're fairly small, 5% or less, hopefully. Okay, so that's question 1. And make sure you show me all these calculations. Show me these 4 ratio calculations and show me the 4% experimental error calculations. Okay, part 2, now we're gonna still look at reflections from mirrors, but now we're gonna look at concave and convex mirrors. So here's an example of a concave mirror. Okay, so the light is coming in to the inside curved part. And you can think of this as you have beams of light which are coming in parallel. I have 5 here. When I do the demonstration, you'll see in the video that with the laser box, it was too difficult to get 5 beams, so we have 3 beams coming in. But what happens is the beam comes in, it reflects off of that concave mirror. So it's doing something like this. This beam comes in, reflects off. The one in the center is going to reflect right back on itself. And it turns out that all of these rays, these reflected rays, are going to meet at one point. They're going to intersect at one point. And this is called the focal point of that concave mirror. Okay. And then the vertex, the V here, is sort of just like the center of the mirror. And if you measure the distance from the focal point to that vertex, we have what's called the focal length of that concave mirror. Now, one thing I'd like to show you is that just like with the plane mirror, the angle of incidence equals the angle of reflection. But in order to figure out that angle, what we have to do is we have to draw a tangent line to the curved mirror at the point that the beam hits the mirror. So actually, let me see if I can do that with annotation here. Yeah, this should work. So something like maybe that for the first one. Let me move it in a little bit. So it's a tangent line just to that point right there. And then if I draw a perpendicular to that tangent line or that tangent plane, so that would be like that, let's say. Then if you were to measure this angle of incidence relative to that perpendicular and the angle of reflection relative to that perpendicular, those two angles should be equal, right? So it does hold that the angle of incidence should equal the angle of reflection. Okay, so now let me get rid of this. All right, now we have the opposite situation. We have a convex mirror, which is just really the opposite side of that concave mirror. So now the light is coming in parallel and it's going to reflect off, right? Again, if I draw a tangent line and then a perpendicular to it, the angle of incidence equals the angle of reflection. But in this case, it reflects off in such a way that the rays diverge away from one another. And of course, the one in the middle is going to go back on itself. And then if we take these rays and we extend them backwards, they all appear to come from one point, right? So these dashed lines are just the extension of those rays backwards. And that is the focal point of that convex mirror. And then if I measure the distance from the center of the mirror, the vertex, to that focal point, that's going to be the focal length of that convex mirror. Okay. And then the other thing that we need for this experiment is we need the radius of curvature, like the radius of these mirrors. So the way that I did this was I traced out the mirror, right? For the concave, I traced out the inside of the mirror. For the convex, I just traced out the outside of the mirror, so it's slightly larger radius. And then I drew two tangent lines, and they don't have to be anywhere special because we're assuming this mirror is circular. So I drew two tangent lines, in this case, one here, one here. Then using a protractor, I drew a line perpendicular to that tangent line, another line perpendicular to that tangent line. And where they cross should be the center of that circle. So the distance from that center to the mirror is the radius of curvature, right? It's the radius of the mirror. Okay, so what you want to do for this part is you want to go look at my video on how I collected all the data for the concave and convex mirrors. And then you want to answer question 2 here. So actually, here's the table. This was the data that I got for the experimental focal length that I actually measured from my pictures. Again, you'll see that when you watch the video. So 2.4 centimeters for the concave and 2.7 for the convex. So question 2, you're asked to compute the theoretical focal length for the concave and convex mirrors, but that's simply going to be half of the radius of curvature. So in that video, you'll see where I did the experiment to measure the radius of curvature for both of them. So if you divide by 2, that will be the theoretical focal length. So you can find these two values. And then you want to compare the two by computing the usual 2% experimental errors. And make sure you show me all 4 of these calculations. Okay, so that's question 2. All right, then the next part, so that was reflection, right? Plane mirror reflection and concave convex, like the curved mirror reflection. Now we're going to talk about refraction. So first of all, what is the index of refraction? What does that mean? Well, it's defined to be a ratio of the speed of light in a vacuum, which is c, and that's a constant, right? Nothing can go faster than that speed. It's around 3 times 10 to the 8th meters per second over the speed of light in the medium. So v is the speed of light in whatever the medium is. Okay, it could be air, it could be glass, or it could be water. It could be many other things too, but those are the things that we're going to deal with in this lab. So either air, glass, or water. Now it turns out that the speed of light when traveling through any medium other than a vacuum, it's always going to travel slower. So v is always going to be less than c. So that means that n here, right, if v is less than c, that means n is always going to be greater than 1. It'll equal 1 if v happens to be c, right? If it's the vacuum itself, then n equals 1. But for anything else, even air, although it's very close to 1, n is very close to 1 for air because v is very close to c in air, but it's slightly slower even when light is moving through air. So n is like slightly greater than 1. But for other things like glass or water, we're going to find that n is larger. For glass, it's around 1.5. For water, it's around 1.33. Okay, so n is always greater than or equal to 1. Okay, so what does the law of refraction tell us? Well, let me show you the picture here, the diagram here. So think of this medium right here up here as being air, and this medium being something else, in this case, say water, right? Or maybe glass. So we have this ray coming in. This would be, theta 1 would be the angle of incidence. And when it hits that boundary, part of the light is going to be reflected. So this theta 1 prime is the angle of reflection. And we know that the angle of reflection should equal the angle of incidence, right? Equal theta 1. So theta 1 prime should, in theory, equal theta 1. And then part of the light that goes to the new medium is going to be refracted. Now, what does it mean to be refracted? It means it's going to be bent either towards this normal or away from the normal. Now, it turns out that if the light is going from an index of refraction that is smaller to one that's larger. So remember, air, the index of refraction for air is around 1. It's pretty close to 1. And water is going to be around 1.33. So it's going from an index of refraction that's smaller to one that's larger. Well, what's going to happen is this light is going to bend towards the normal. So this theta 2, this is what we're calling the angle of refraction, and it's going to be less than the theta 1, which was the angle of incidence. Okay, I could also turn this around and I could say, imagine that these arrows are reversed and I start in water. So now I'm starting at a higher index of refraction, and then this is my angle of incidence, theta 2, and I go into air, which is the lower index of refraction. What's going to happen? It's going to bend away from the normal. So in this case, the angle of refraction would be greater than the angle of incidence. Okay, now there's a formula, right, discovered by Snell that relates the angle of incidence, the angle of refraction, and these two index of refractions together. It's called Snell's law. So what it says is that if I multiply the index of refraction in the first medium times the sine of the angle of incidence, that's got to equal the index of refraction in the second medium times the sine of the angle of refraction. Okay, now what we're going to do, so think of N1 as being the index of refraction of, say, air, and N2 is being the index of refraction of water. So, or it could be glass as well. We're going to want to know the ratio of the index refraction of water relative to air, or the ratio of the index refraction of of glass relative to air. So in this case, I'm calling that N2, 1, that's the ratio of the index of refraction of medium 2 to the index of refraction of medium 1. So if we solve this, N2 divided by N1, that's going to be sine of theta 1 divided by sine of theta 2, right? And I've done it for you here. So often we're just going to compute the ratio of the index of refractions. And the reason why we do that is N1 is the index of refraction of air, and it's pretty much equal to 1 anyways. So when I compute this ratio, I'm basically finding the index refraction of the other medium, whether it's water or glass. Okay, so Snell's law, that's going to be important. It relates the index refraction and then the angle of incidence and angle of refraction. Okay, so make sure that you watch my video on how this data was collected. This was done on a prism. So let me show you the picture here. So here is a triangular prism, right? And it's an equilateral triangle. So the laser beam ray was coming in like from the left here, and this medium is air, right? So the first boundary, it's going from air to glass. So you can think of this angle, remember the angles are always measured relative to the perpendicular, so the dashed line here is perpendicular to that face, the boundary. This I1 is your angle of incidence, right, for that first boundary, for the first face here. And then when it goes from air to glass, it's going to refract, it's going to bend towards the normal. So R1 is going to be less than I1, so it bends towards the normal, because it's going from an index refraction of air, which is like 1, to one of glass, which is higher. It's around 1.5. So I1 is the angle of incidence. R1 is your angle of refraction. Then for the second face, right, think of it as like two different problems. It's first going from air to glass, and then think of it as starting in the glass and going back to air. So for the second part, I2 is like your angle of incidence, right? When it starts in the glass, this is your angle of incidence. And then when it goes to air, where the index of refraction is smaller, it's going to bend away from the normal. So R2 would be your angle of refraction. So angle of incidence, angle of refraction. So think of I as incidence, R as refraction. So for this part of the lab, I measured these angles for you. And angle A here is called the prism angle. And I measured that using a protractor. But in theory, right, if this is an equilateral triangle, what should the angle be? It should be around 60 degrees, right? In theory, it should be exactly 60 degrees. Okay, so if you look at the table here, these are my measurements. Actually, I measured exactly 60, and you'll see that in the video. And then these are really difficult to do. So probably the most error in the lab is going to be consisting of measuring these angles right here. But I did the best I could, and these are the values I got. So I1 for this angle, I got around 46 degrees. For the angle of refraction for the first face, I got around 23 degrees. I2, so the angle of incidence when I'm in the glass now, is 35. And then R2, the angle of refraction when I go back into the air, is around 55. Okay, so question 3. What I want you to do is compute the index of refraction for glass relative to air for the first face, like using this information, and then for the second face. So how do you do that? Well, you're going to have to write this out, right? Think of Snell's law. It's saying that n air times sine of I1 has to equal n glass times sine of R1. So if you solve that for n glass over n air, you're going to basically get sine I1 over sine of R1. But make sure you do that out, right? So it's really going to be the sine of I1 divided by the sine of R1. That'll give you this value. Then for the second phase, think of this as n glass times sine of I2 equals n air times sine of R2. So again, we're just using Snell's law. So if I solve for n glass over n air, in this case, I'm going to get this is equal to the sine of R2 divided by the sine of I2. Okay, so the i's and r's kind of switch roles in this case. So this would be the sine of R2 over the sine of I2, and that'll give you that value. In theory, the index diffraction of glass is around 1.5, so you should be getting around 1.5. When I did this, I got a little bit higher here, but that's okay, right? So theory, they should be around 1.5. All right, then theoretically, it turns out that this prism angle, so this angle A, should equal R1 plus I2. You could show that using geometry, okay? So this angle A should equal R1 plus I2. So based on the angles that I measured in my video, you want to calculate what A is from that formula. Basically, you're just adding these two together, right? These two angles together to get A. And then compare what you got from the formula to what you actually measured, which we measured to be 60 degrees, by computing the percent experimental error. Okay, so think of the formula as the one as your gold standard, right? The one that you want to divide by, your accepted value. All right, part 4. So actually, this was a really quick part. In this case, I had a double convex lens and a double concave lens. And I set up the ray box so that 3 rays were going through those lenses. And based on what you observed, I want you to describe whether the double concave and the double convex was either converging or diverging. So you just have to write in here whether it's converging or diverging. And I kind of give you the answer in the next part. So for part 5, so the double convex lens is basically a lens consisting of two, you can see it right here, consisting of two convex sides. So convex, convex. And you can think of it as it's thicker in the middle, thinner at the edges. So thicker in the middle, thinner at the edges. And what should happen with a double convex lens? Well, if light comes in parallel, so I have 5 rays come in parallel, when it hits the glass, it's going to refract. Actually, it won't go straight to the center here. I just did that because it was easier to draw it that way when I was making these. What's really going to happen, as soon as it hits the glass, it'll refract, it'll go in a straight line, and then when it goes from glass to air, it'll refract again. And it turns out if the rays are coming in parallel, they're all going to refract so that they end up passing through one single point here, and the one in the middle just goes right through. So they all intersect at this one point. This is called the focal point of that double convex or converging lens. So this would be the focal point. And then the focal length is from the center of that lens to that focal point. So that length in centimeters is from here to that focal point. Okay, now a double concave lens. So I have a concave side and then a concave side. This turns out to be a diverging lens. Parallel rays coming in, right? The one in the middle is going to go straight through. The other ones are going to refract in such a way that the rays diverge away from one another. However, if you extend these rays backwards, they all appear to come from one point. And that point that they appear to come from is the focal point of that diverging lens. So the focal length is from that focal point measured to the center of the lens. So that length in centimeters would be the focal length of that diverging lens. Now, just out of convention, the focal length for our converging lens, so again, the measurement from here, center of the lens to that focal point, is going to be a positive value. And then for a diverging lens, because the light doesn't actually meet there, it just appears to come from that point, it turns out by convention, it's a negative value for that focal length, okay? And basically the goal for this part of the experiment is to measure the focal lengths of converging and diverging lenses. Okay, so what happens now if we take a converging lens and we have some like object that's illuminated? In this case, it's going to be like an arrow. So let me show you that picture here. So we have an object, right? There's like a light source so we can see the object well. I have a converging lens, and over here I am going to have a screen so that I can focus the image onto the screen. Now, how do we know that the image is going to appear over here? Well, we can follow a couple of these rays, right? Remember, there's many, many, many different rays coming off of all parts of this object. I'm just tracking 3 of them. So the one that leaves the tip of the arrow and travels parallel, when it goes through the converging lens, remember, it's got to go through the focal point, right? So it passes through the focal point. The one that goes through the center just travels right through the center. And then the one that passes through the focal point on this side would have to emerge parallel, because if I did it backwards, if I went this way, right, parallel, it'd be refracted and would go through this particular focal point. So if I go backwards through the focal point, it's going to emerge parallel. Now, where all 3 of these rays intersect, that's got to be the tip of the arrow for the image. And notice that the image is inverted, right? So it's going to appear on the screen. When you focus on the screen, it'll appear upside down. So it's inverted. So converging lenses are going to create an inverted image here. All right, now there's a relationship between the focal length of that converging lens. So remember, that's from the center of the lens to the focal point. So that's F. And then what we call the object distance, that's from where the object was situated to the center of the lens. So I'm calling DO the object distance. And then the image distance is from the center of the lens to the screen where the image is focused, like it's focused crisply on the screen. Okay, so that would be the image distance. So what is the relationship between those 3 variables? Well, it's called the thin lens formula, and it's given right here. So it turns out that 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. Or if you just rearrange this algebraically, it's going to be easier because we're going to want to solve for F. So I just solved this for F. You can do this yourself, right? Multiply by the lowest common denominator, which is F times DO times DI, both sides. And when you rearrange it, you're going to find that F is equal to the object distance times the image distance divided by the sum of the 2, right? Divided by object distance plus image distance. This is just, they're both the same. This is just an easier formula when you're plugging in numbers, okay, if you want to find the focal length. So this is a formula, thin lens formula, that relates those 3 variables together. All right, the other thing that we're going to want to look at is something called the magnification. Like, what does the lens do in terms of magnifying the object? So there's a couple of ways we can think about magnification. In theory, right, the magnification is simply defined to be the ratio of the image size to the object size. So what do I mean by size? I basically mean the length of that arrow, right? So if I were to measure the length of this arrow on the image and divide that by the length of the arrow from the object, that's going to be the magnification. And the negative means that it's inverted. So when the magnification is negative something, the negative just means it's flipped. The image is inverted relative to the object, okay? So that's one way of doing magnification, just simply by definition. It's the length of the image divided by the length of the object. And since it's inverted here, it's negative, whatever that ratio is. The other way you can do it is you can use these values, the object distance, DO, and the image distance. So, and again, this comes from like basic geometry, basically from similar triangles, I guess. It turns out that the magnification is equal to negative, that tells you it's inverted, and then it's just going to be the image distance divided by the object distance. So if you know this image distance, which we have from our data, and the object distance, which we have, then you can calculate the magnification that way as well. And I'm going to have you guys calculate it in both ways. Okay, what about, so that was a converging lens, right? A double convex lens. What about a diverging lens, a double concave lens? What happens here? Well, in this case, right, so here's my object, the illuminated object. I'm going to track three rays again. So one leaves the tip parallel, and when it refracts through the lens, it's going to diverge away as if, right, if you extend this backwards, it appears to be coming from the focal point of that diverging lens. It goes out. The one through the center passes right through the center. And this one's a little more confusing to me. I have to think about this a little bit. The one that would appear to go through the focal point on this side would emerge parallel. I guess that makes sense because if I came in this way parallel, right, it'd be refracted in such a way that if you extended it backwards, it would go through this focal point. So if we go from the other way, it's going to emerge parallel. Now, if I extend all these rays backwards, so dot, 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 it's all the dashed lines in this one, they intersect at one point here, and that's going to be the image of the tip of the arrow there, right? But this is not a real image. Like, I can't put a screen there. I can only put a screen on this side, right? The light appears to come from there. It's not actually meeting at that point. It just appears to come from that point. Like if you look through this lens, from if your eye's over here and you look through the lens, you'll see the image there, but there's no way of putting a screen there to measure where the image is. The light is not being focused at that point. It's just appearing to come from that particular point. Okay, so that's why we call this a virtual image, right? A real image would be like this. On this side, we can put a screen there and all the light is focused on that point. So that's a real image. In this case, we have what's called a virtual image. Okay, so the problem is going to be, because we remember ultimately we want to find the focal length of this diverging lens as well. But if I can't put a screen there, how am I going to figure out the focal length of this diverging lens? Well, we're going to do we're going to trick it a little bit. In addition to this diverging lens, we're going to put in a converging lens. Actually, it'll be the 10 centimeter converging lens we're going to place in here. So we're going to put both lenses in together. And when you do that, you're going to get a situation like this. If I put a combination of both lenses, where I have an actual image on the other side, and I can move the screen there and focus that image. Okay, so we're going to combine the 10 centimeter converging lens with this diverging lens. Think of them as being placed together. And then we'll get a situation like this where we can figure out DO and DI. Right? And we'll use that later to find the focal length of this diverging lens. I'll explain that in a minute. Okay, so again, look at my video on how I actually collected this data. Right? You can go to that link. For the first part of the experiment, the object distance is set to be 20 centimeters from the lens. Okay, so basically what I have here in the first table is the location of the lens. I just left the lens, I had this like bench, right? And it has a meter stick on it. And I left the lens holder, which has the lens in it, at 50 centimeters. And I put the object at 30 centimeters. So that means this object distance, DO, and I filled it in for you, has to be 20, right? So that's set to be 20. Then I moved the screen, and again, you guys will see this in the video. I moved the screen so that the image was focused, And then I can take that location, right, wherever the screen is, and subtract the location of the lens, and that will be the image distance. So I'll have you guys calculate that. And then once you have that, then we can calculate the focal lengths of that converging lens. In fact, we actually did this for two different converging lenses. We did a 10 centimeter converging lens and a 12.5 centimeter converging lens, right? So that's lens one is a 10 centimeter one, lens two is a 12.5 centimeter one. So using the thin lens formula, you're going to calculate the focal length for both of those double convex or converging lenses. And then you want to compare what you got, your calculated value, to the accepted value of 10 and 12.5, right? By computing the 2% experimental errors. And again, show me these four calculations. Okay, then we wanted to look at the magnification. So I measured, again, and you'll see this in the video, I measured the size of the image, that arrow, with a ruler, and I got around 3.4 centimeters, right, for both of them, because that doesn't change. Then on the screen, when the screen was focused, I measured the size of the image, and I got 3.3 centimeters for the 10 centimeter converging lens, and I got 5.4 centimeters for the 12.5 centimeter converging lens. So I want you to calculate magnification two different ways. Calculate it by the definition. It's just going to be the image size divided by the object size. Okay, so you'll get those two values. And by the way, you want to put a negative there because the image was inverted in both cases. And then calculate it using the formula. Remember that formula came from basically similar triangles from geometry. So it's just negative di divided by do. And you have the di and dos from this table up here. Okay, and they should be pretty close. And again, they're going to be negative. Well, actually, in this case, the negative is built into the formula. And then compare these two by computing a percent experimental error. Now, it's a little confusing when you're subtracting with negatives here. So what I would do when you compute the percent experimental error is just compare the absolute values, right? And then divide by, let's agree that the formula is our accepted one. So subtract, find the difference, and again, just worry about their absolute values, divided by the absolute value of the formula 1 times 100, and that'll be the error. And again, show me these 6 calculations. Okay, so now the last thing we want to do for this part is determine the focal length of that diverging lens, right? The double concave diverging lens, which, remember, did not have a real image. It had a virtual image. So we had to play the little game there, and we had to first, we had to put a combination of two lenses together. We had to put the unknown diverging lens with the 10 centimeter converging lens. And once we did that, then you actually get an image on the right-hand side. So what you should do is the following. So again, if you look at my video, this is the data. So the location of the lens is at 50. Now the location of the object is at 10, right? So we set that object distance to be 40 centimeters. So I did that for you here, right? 50 minus 10. It turns out that the location of the image for that combination of the two lenses is 88. So now you can find DI, right? It'll just be the image location minus the location of the lens, right? That'll be DI. And then what you want to do first is you want to make sure you compute F combo. So this is the focal length for the combination of those two lenses. Because remember, now that the image is a real image on the right-hand side, there's going to be some focal length for that combination of the two lenses. Well, to do that, you just use the usual thin lens formula. So DO times DI, object distance, times image distance, divided by object distance plus image distance. And you have that information here, right? So compute F combo first. Then we have to use that other formula that involves the focal length if you have a combination of two lenses together. So that came from, let me go back to that for a second. I think I have it up here. Yeah. So it turns out that 1 over the focal length of the combination of the two lenses is simply equal to 1 over the focal length of the converging lens plus 1 over the focal length of the diverging lens. So to make this formula easier, because it's harder to use it when it's sort of in this inverse form, I solved this for F diverging, because that's ultimately what we want to find. So if you multiply both sides by the lowest common denominator and solve it for F diverging, you're going to get this formula. It's simply F combo times F converging divided by F converging minus F combo. Okay. So once we have F combo, this is the formula you want to use to find F diverging. So let me go back to that problem. Okay, so once we have F combo, and you got that just by using the usual standard thin lens formula, using DO and DI, then we can plug that into this formula to get our F diverging, which is what we really want. Now, what is F converging? Well, remember, we put the 10 centimeter converging lens in combination with that diverging lens. So F converging is just 10. You just have to plug in 10 here. And F combo is whatever you calculated for your F combo here. Okay, and that'll give you F diverging. And you should get something, it'll probably be like negative 20 point something or negative 21, something around that. So then compare these two by computing the percent experimental error and show me these calculations. Okay, then I thought it might be fun because we didn't get to do much, or you guys at least didn't get to do many measurements. I thought it might be fun to actually do a few of these things with some really well-written simulations. So I thought that the last two parts of the lab, I would do a couple of simulations. Okay, so part 6, this is gonna be the prism refraction simulation. So this is very similar to what I actually collected in my video in terms of the prism, but I want you guys to do it using the simulation. So here's the link to the simulation, and then let me bring that up and I'll show you how to do this part. It's basically gonna be the same table that you had before, but now we're gonna figure out what all these values should be. Okay, so let me bring that up. Okay, so here's the website. Again, I'll give you guys the link. For some reason, the prism simulation didn't record correctly, so let me go over that right now again. So you're going to go to that website from the link that I provided, right? The bending light simulation. You want to double click on it and then go to prisms. So here's the laser beam, right? We can move this around. Right? It fires a single ray. And for this simulation, we're going to, this is the one where we're going to do an experiment with the prism, and it should match very closely to what I actually collected for the data. So you want to grab the prism, the triangular prism, and if we shine a ray through it, right, it's going to refract. So think of it going from air to glass. So when it hits that boundary, it refracts, and then glass back to air again, it's going to refract again. And what I would do is I would rotate this prism so that the line that's passing through the glass is pretty much parallel to the base of the prism. Okay, so something like that is good. And then since we want to make all these measurements, we need the lines that are normal, that are perpendicular to the two faces. So if you click on normal over here, normal lines, it gives you those lines. And then to measure the angles, we're going to use a protractor. So if we click protractor, and then we can drag the protractor. Now remember, there's 5 angle measurements you want to make, right? You want to measure the prism angle. So this angle right here. So if you bring the protractor up, somewhere like right there at the peak, and then you can rotate it. If you grab on the edge here, you can rotate it. So I'll set this side at 0, and then if I read off this side, it should be 60. It looks like it's right on 60. So we're showing that this angle is 60 degrees. Okay, and then all the other ones, these are a little tricky to measure. You're gonna bring the protractor down. What I would do is maybe put the 0 where the dashed line is, and then do your best to read this angle. So that would be like I1, right? That would be your first angle of incidence. Then you would measure this angle right here, which would be R1, right? Your first angle of refraction. So that would be the two angles for the first phase, right? Angle of incidence, I1, angle of refraction, R1. Then think of it as you're starting in the glass now. So this is I2. So you'd measure that angle, I2. And then the angle that this makes with the perpendicular would be R2. So those would be your two angles for the second phase, right? Angle of incidence, angle of refraction. So just like I did before when I experimentally measured them, the angles of the protractor and then drew it out with a marker, you're just gonna do that now using this protractor in the simulation. Okay, I don't know why this, I guess I accidentally didn't press record or something. So put this section where I first talk about the simulation of the prism. Great, thanks. Okay, once you have that, you can fill in this table. So I1, R1, I2, R2, and then angle A, the prism angle that you measured. And then questions 9 and 10 are basically what I asked earlier, but now you're going to use your simulation data. So you want to compute the ratio of the index refraction of glass over the index refraction of air, right? For the first phase and then for the second phase. Remember, in this case, this is going to equal the sine of, let's see, I guess it's a sine of I1 over the sine of R1. In this case, it's going to be the sine of R2 over the sine of I2. And it should be a lot better, more accurate than what I did when I measured it, using a marker and a protractor. In theory, the index diffraction of glass is around 1.5. So you should find that you get values that are much closer to 1.5 than probably we got experimentally from before. Okay, then question 10 was calculate the prism angle theoretically. Well, that was simply R1 plus I2. So whatever you measured in the simulation for R1 and I2, just add them together. That's going to be your A formula, and then compare that to what you actually measured from the simulation using the protractor or the angle itself. And we got around 60, and hopefully this is pretty close to 60. And then compute that percent experimental error, compare these two values. These you don't have to compare, just maybe comment on the fact that hopefully they were close to 1.5. Okay, and then the last part of this experiment is another simulation, because I wasn't able to, it wasn't really easy to collect or to show you guys how to collect this data. This is something we do, it's called a refraction tank, where now we use water as our medium. So we're going from like air to water, but it really wasn't easy to show you this. So I figured we'll just do it through a simulation. So you're gonna go to that simulation again. And given these 6 angles of incidence, you're going to measure the angle of reflection and the angle of refraction. Okay, so let me show you how to do that. Okay, so basically it's the same simulation, except now instead of prisms, we're going to go to intro. You can do it on the bottom here, or you can just back out of this. So you want to go to the intro part now. Okay. Here, this material in the white is going to be air, and the one in the blue is going to be water. That's the default, so make sure that you keep that. So air into water. Now we can vary the angle, right, of this laser beam. So here's the laser beam. You want to grab the protractor tool, set it up so it's like right in the center, something like that. And then when the angle of incidence is 20 degrees, so you're going to set this at 20 degrees. Remember, you always measure relative to the perpendicular, right? So this is 20 degrees. So given that, you're going to measure the angle of reflection, which is this angle. And actually it looks like 20, right? Which makes sense. It should be exactly the same in theory. And then you want to measure the angle of refraction, right? And that's a little more complicated because that really depends on Snell's law to figure out that. So this is set to be 20, measure the angle of reflection and the angle of refraction. And again, these are all measured relative to the perpendicular. So that would be this angle, the refraction, and this would be the reflection. Then change this to 30. Do the same thing. And then 40, all the way up to, I guess I did 70, right? So 20 through 70. Okay, so that'll give you all the data that you need. Now let me go back to the handout. Okay, so once you have all of that data, then you can fill in this table. So these were the given, right, angle of incidence values, so 20, 30, 40, 50, 60, 70. The second column is going to be the angle of reflection, and these will probably be very similar, right? And the third column here, what I want you to do is to compute the ratio of the angle of reflection, so theta 2, to the angle of incidence. So you want to divide these two, right? Find those ratios. Now we know that in most cases they're going to be very close, if not exactly equal to 1, right? So you should probably get something very close, if not exactly 1 there. Then you're going to average those. So average those 6 values, and then compare that average to, think of this as like your experimental value, compare that to the accepted value, which should be 1, right? That ratio should be exactly equal to 1. And you'll compare them by computing the usual, percent experimental error. Make sure you show me that percent experimental error. Okay, then in the second table, so same 6 angle of incident values, but now you're going to fill in the angle of refraction, right? When it goes from the air to the water. So this is the angle of refraction. And now using Snell's law, I want you to compute the index of refraction of water relative to air. Okay, so N water divided by N air, which we call N2, 1 in this case. And actually in the question, I read out exactly what formula you want to use. So it turns out if you use Snell's law, you can derive that ratio, so this is basically N water over N air, which we're calling N2, 1. It's simply going to be the sine of the incident angle, theta 1, divided by sine of the refraction angle, right? So it'll be the sine of 20 divided by the sine of whatever you got for the first angle of refraction, then sine of 30 divided by the sine of this angle, and so on. So you want to compute all of those index of refraction ratios, then average them together. Okay, so average those 6 values, and then compare that average to the gold standard or the accepted value, which is going to be 1.33. Why 1.33? Because the index of refraction of water is around 1.33. And remember, the index of refraction of air is very similar to that of a vacuum. It's almost exactly equal to 1. So 1.33 divided by 1 is still 1.33. So you'll compare your experimental value, your average, to 1.33 by computing the percent experimental error. And then again, make sure you show me those calculations. Great, that's it. So this lab kind of combined 2 labs together. Normally, if this were an in-class lab experience, we would have done 2 labs on optics. There's one thing that I didn't talk about, which was dispersion, but we also did a few extra things looking at the the simulations. Okay, so after this, there's only going to be one additional lab left. It'll be lab 9, and that'll be on circuit analysis. So Ohm's law will be analyzing basic circuits. And then at the very end, there'll be some sort of lab exam on these three labs: wave motion and sound, geometric optics, and then the circuit analysis stuff. Great, thanks.